Join the conversation.
You're with Cape Talk.
At 9:35 exactly, Views and News Friday, just after 9:30, a huge appointment with, of course, none other than Dr. Chris Smith, the Naked Scientist. He's joining us via Zoom from London, and he's here to answer your questions. A warm welcome, Chris. Great to have you back.
Hi, Clarence. Cambridge, actually. But what's 80 miles? No, 80 kilometres between friends. Not far, yeah. But Cambridge is the centre of the universe, you know. Copernicus had it wrong. The universe does not rotate the way he thought. It's actually the universe rotates around Cambridge.
Yeah, no, absolutely. I got that horribly wrong. But look, let's start off with, I think, a very loaded question. It comes in from Solly in Wynberg. It reads, not actually a question, yeah, a loaded question it is. But can you share your thoughts on an article I read on the UK's independent website on the Trends in Ecology and Evolution journal that ethanol consumption amongst animals in one 2012 study, male fruit flies were found to increase their alcohol consumption after being rejected by a mate, while females of a closely related species were found to be less selective in their choice of mate after consuming ethanol.
I did see that headline. It was very clickbaity in journal terms. Even science PR can be clickbaity. And we've known for a long time that animals succumb to alcohol the same way we do. And when many insects go and eat fruit, because that's where even mosquitoes don't just drink blood, only the females do that anyway, but mosquitoes get most of their energy by going and finding mouldy pieces of fruit, and then they suck up the juices. And anyone who's walked through an orchard in autumn will know that smell, almost like cider, of fermenting fruit. The rotting fruit on the ground has yeasts on it, and it is becoming a bit alcoholic. So anything that's eating the fruit is getting a bit of a dose of alcohol. And so, yes, animals have always been exposed, not through choice or volition necessarily, but through necessity of going and getting their lunch. But the question is, do they do this in order to change their behaviour? We drink alcohol as a social thing and also to change our behaviour a bit. In some people's cases, a lot. And sometimes of the year and some days of the week more than others. But do animals actually do this intentionally? Well, that's very hard to prove, isn't it? Because you can only say what you can observe and draw conclusions from the association. You can't say one thing causes the other. But if you've got an animal that has tried to mate and failed, it might be it's been rejected because it's not big enough. So what do? You go and eat. Well, what do you eat? You go and eat fruit juice that happens to have some alcohol in it, and that may make a difference. On the other hand, maybe they are just drowning their sorrows. Who knows? The other interesting thing about booze, I learned this a few years ago, goldfish and members of the carp family that live in ponds that traditionally freeze over in winter have a quirk of their metabolism that means that they can divert the waste products of their metabolism into making alcohol. So these fish pee alcohol into their pond when there's low oxygen conditions. So they will get a little bit drunk over winter, although given it's literally a drop in the ocean for them, it won't make a huge physiological effect. But it was an interesting discovery by researchers at John Moores Liverpool University about 10 years ago, and they did actually show that these animals get round the low oxygen environment by shunting metabolism into the production of alcohol, and they pee out the booze, and that enables them to scavenge a little bit more energy without any oxygen. So alcohol has been inveigled and intertwined with our evolution and other animals' evolution for millions of years.
Michael, the question that keeps him awake at night is as follows. Please ask the doc to satisfy my curiosity. When I pass gas, sometimes the sound is loud and sometimes it's just a hiss. Why?
Everyone does it, men and women, equal times of the day, about 12 times a day on average, and each one is a couple of 100 millilitres at most. Probably a bit less than that. In some people's cases, certainly a lot more. And the answer to this question is it will come down to the volume, because not all farts arrive in similar proportions. Sometimes it's little pockets of gas, sometimes much bigger volumes. And the amount that you dispense at each sort of sitting, as it were, is going to make a difference to how open the aperture is, because the gas is there that needs to come out. If it needs to come out all in one go and it's under high pressure, it will open things up to a different extent than little bits of gas that can be snuck out through a small hole but without much turbulence. Because what makes a noise is turbulence. If you think about taking a really deep breath, if you take a deep breath in really quickly, it makes more noise than if you take a similarly sized breath in but more slowly. Why? If you do it more slowly, the velocity of the air is lower, and if you have air moving at a lower velocity, it does not exceed something called the Reynolds number, which is proportional to the size of the thing that the air is flowing through, the tube. And if you exceed that number, you get turbulent flow. If you get turbulent flow, you get a rushing noise. So a really raucous ripper fart is probably going to be big volume, but it's going to be going through a fairly tight aperture, fairly fast, and making a big noise. Small volumes of gas are probably going to go through a small aperture, but they're going to come out probably a bit more slowly because the pressure's lower, and they'll probably come out in a way that is less obvious, let's say, which is where the silent but deadly gets into the equation.
A ripper fart, okay, is silent violent?
Well, silent but deadly, or silent but violent, I think was the saying we used to use in school. And those are usually the highly sulphurous ones, the ones that are fueled by cabbage, Brussels sprouts, cauliflower, vegetables with lots of sulphur in the plant. Because when this ends up in your intestine, it gets metabolized by the bacteria, and we can't use those sulphur compounds, but the bacteria can, and they produce odoriferous byproducts, including hydrogen sulfide and also one called methyl mercaptan, which is the same stuff that skunks fart out and spray out of their rear end in order to deter you from pursuing them. And these are part of the odoriferous bouquet that is what makes a silent but deadly fart smell the way it does.
Okay, Ray's got a question about gravity. The question is, what is the most appropriate action to take if a lift's cable snaps and plummets several floors with you and others still inside it? What's that? Make peace with your God, I guess, huh?
Aye, Ray, I was going to say put your hands together and pray. First point, lifts have built into them, since the time of Schindler, who actually was one of the most prolific producers of things like lifts for decades. But built into lifts is a special ratchet mechanism. So when the cable pulls and the lift is under load, the ratchet pegs which stick out from the side of the lift into the lift shaft are withdrawn in. But if anything unloads the cable, and therefore the lift is potentially in a free fall position, there's nothing pulling on a giant spring those ratchet hooks inwards from the sides of the lift. So they spring out and they engage with gaps on the sides of the lift shaft, stopping the lift from falling. So a lift, all being well, and it's being made properly, cannot go into free fall. Even if the cable snapped, it won't do that. But let's assume that in Ray's scenario, it can. If you're in a lift, you are falling as the lift falls, and it's as though you have jumped off a building. And you are in free fall inside the lift. So people often say, well, why don't I just jump the minute the lift hits the ground? Because then I will be moving upwards as the lift goes splat, and that would offset the effect. But the reality is that that would be like you saying, well, I'm in free fall off a building. How do I stop myself going splat when I hit the ground? Well, you'd have to accelerate yourself off the bottom of the lift with a jump which would give you an equivalent amount of energy as the energy that you have effectively now got, which is free fall energy, kinetic energy of you at terminal velocity, and you'd got to do that incredibly quickly. So you'd have to basically accelerate yourself as though you could jump over a house. That's the way of thinking about it, because you've got to have the equivalent amount of energy that you started with in order to offset the momentum downwards. So unless you are a pole vaulter with incredible leg muscles and capable of jumping over a house like a flea can, then you are never going to be able to offset the momentum in the opposite direction, so that you are literally in a neutral movement position when the lift goes splat. So unfortunately, I think your suggestion to put your hands together and meet your maker is probably the only answer if you're genuinely in free fall under those circumstances.
Sure, that roof is going to crash into the floor anyway.
Yes, the lift will crash into the floor and you'll be crashing into the floor with it. But unless you can go in the opposite direction to the lift and very, very quickly and know when the lift's about to hit the ground, you're never going to offset the momentum so that your momentum is the opposite of the lift's or the momentum you previously had. So you will still go splat.
The Naked Scientist on Cape Talk. It is 9:45. Your questions via WhatsApp 072-567-1567. Leave a voice note or a text note and we'll get to it. Better still, give us a call 021-446-0567 and we'll prioritize your call. Mark Bright has the following question. Could you please ask Dr. Chris about the two Earth theory? Were there really two Earths at one point in time?
I think what Mark might be referring to is the question of, and this is a sort of detective story, when we look up into space, we see Earth's moon. And when we look at the rocks that the Apollo missions have brought back from the moon, and we date them about 4.5 billion years, same age as the Earth. And when we look at other planets like Mars, very similar to the Earth, they have moons, Phobos and Deimos, but they're very, very small. Our moon is huge compared to other moons and compared to our planet. So when you put all that together, you've got a moon made of the same stuff that the Earth crust is made of. It's got a similar age to what we call the current planet Earth, and it's disproportionately big for the size of our planet and where it is. There's no way we could have caught that as a moon coming in from somewhere else, so it must have got made. How did it get made? Well, the theory is that way back about 4.57 billion years ago, there were two planets which, for various reasons, one probably a bit smaller, one a bit bigger, Mars size, Earth size, ended up on a collision course in space. And one rammed into the other. The two planets merged, but in the course of the collision, which melted the new planet and made a completely molten ball in space, ejected a whole load of the surface material of what was then the Earth into space around this ball of molten material, and that ejector then coalesced to form the moon as we see it today. And that's probably where this two-planet idea comes from, and they notionally call the other planet that hit us about 4.5 billion years ago Theia. So I think that's what Mark's referring to.
Let's go to the WhatsApp line. There's a voice note there, Joe.
Good morning, Clarence and Dr. Chris. Dr. Chris, where do mosquitoes disappear to during daytime, the day hours? I'd like to know where they hide so I can do something about them before they re-emerge at night.
Yeah.
Thank you, Dion Perro.
Hello, Dion. Well, the answer to this is that there are thousands of species of mosquito, and only some of them disappear during the daytime. The ones we tend to talk about the most are the ones most closely linked to the transmission of diseases, including diseases like malaria. And the Anopheles mosquitoes that transmit that are night active, which is why you put bed nets up. If you want to stop yourself getting bitten, you sleep under a net. The mosquitoes then go away during the day, and you're much less likely to be bitten. But other mosquitoes, including Aedes mosquitoes that spread things like yellow fever and dengue and Zika virus, they are day-active mosquitoes. They love also big animals like humans, and they tend to love living in cities. So the problem is, even if you have one strategy that deals with the nighttime active malaria spreading anopheline mosquitoes, you've got a problem with the day-active Aedes mosquitoes. So it will really depend on what species, Dion, you're talking about, because your strategy to control them is going to differ, but some things are common to both. And one of them is mosquitoes are all united in their need to breed over water. Because they lay eggs in water, they turn into little larvae, and the larvae then eat algae and other things in the water to grow into mosquitoes that emerge and then come and bite you. So most of the infection control strategies and transmission control strategies for malaria and dengue and that kind of thing all evolve or revolve around finding pools of water and getting rid of them. So if you can do that by not having pots and pans and water butts and stuff like that, you can stop the mosquitoes breeding near where humans are. And you also combine that with things like strategies to spot them in homes and splat them, and also warn people about sleeping under bed nets if it's a malarious area, and also wearing repellents and so on. But it's very hard to have a one-size-fits-all way to control them. They're amazing as a vector for disease, which is why they have evolved to be that very thing.
A question from T. It reads, Morning, Dr. Chris. I have very mild tinnitus, I assume, in one ear that can only be heard when falling asleep. I think it's tinnitus, but it comes and goes and sounds like a duck softly quacking every few seconds. Can this be tinnitus, as it's not a ringing sound as I thought tinnitus was?
What's more likely is that this is the sound of your own heartbeat. And when you put your ear to the pillow, you block the external auditory canal, the bit you put your finger in and wiggle when you've got an itchy ear. That is the pathway that leads to your eardrum. And when you put your head to the pillow and block that, you invoke something called the occlusion effect. You create a cavity between the pillow surface and your eardrum, and certain frequencies will resonate and therefore amplify in that cavity. And when your blood pulses through your arteries, it will create small movements in all your body's tissues. They expand and contract, because as the blood rushes in, they get bigger, and when the blood leaves in the veins, they shrink a bit. And this makes a noise when you hear it in your ear. So people often think, oh, I've got some kind of ear problem. You're hearing your own heartbeat. And the fact that it's only every second or so is really good, because as you drop off to sleep, your heart rate falls to about 50 or 60 beats a minute in most people. And that is a soothing sound that should help you off to sleep. If you want to get rid of it, roll onto your back, and then you won't have an ear against the pillow, and the occlusion effect will go away, and you won't notice the sound anymore.
We've got a voice note. We've got two there. Let's take a listen, Joe.
Good morning. It's Walter speaking. Please ask the naked scientist what happened with a Teflon scare. At one stage, you said, oh, Teflon is really poisonous, but we're still using it, so I assume it's okay. Thank you. Goodbye.
Walter, I think this is referring to what we call PFAS, forever chemicals, perfluorinated alkyl substances. The way Teflon works is that this is a highly unnatural synthetic substance where you've got fluorine atoms stuck onto carbon chains, and it endows the substance with the exciting properties for which we love Teflon: low stick, high slippage, etc. The problem is, because these chemicals do not exist in nature, there's no mechanism in nature to get rid of them, which is why they're called forever chemicals. Everything else that's made naturally in the world is part of the system where energy flows from one place to another. Things get made, molecules get made, and then other processes dismantle those molecules and recycle both the molecules, the atoms that are in them, and the energy flows through the system. We've come along and created this family of chemicals which do not exist in nature. They've never existed in nature. There is therefore no natural mechanism to degrade them. And what we're seeing is that some of these chemicals are building up in the environment in various places, including processing through the food chain to points where they then come into contact with us. So it's not just your bacon in your frying pan in the morning. They are on and in everything. So when you go to the burger bar and you get your chips in that cardboard thing that holds them, that's a convenient place to put your chips or fries or whatever, the cardboard does not get all greasy, and it's a nice smooth texture because it's covered in these sorts of substances. They're sprayed on there to give them their grease-repelling properties. Problem is, that stuff gets into your chips, it gets into you, it gets into the environment, and when you chuck that in the landfill, or even if you burn it, the things don't disappear. And what we're now finding is they're cropping up all over the world. Even poo from penguins in Antarctica has got this stuff in because it's got into the oceans, it's got into fish, the fish have gone into the penguins, and the penguins are concentrating them in Antarctica. So scientists are worried about this, and they're highlighting this as a risk to the environment, because when you get things building up, there are often unforeseen consequences. And also, when we're exposed to stuff, you've got to be exposed for a period of time before the level of exposure, unless the thing's really potent, has an effect. So we may not have been exposed enough to these things yet to see what all of the health consequences are, but there are proposed to be some. And there are a range of possible health outcomes that could come from this sort of thing, which is why people are highlighting this, and which is why they're then trying to reduce the emissions release and use of these sorts of chemicals to try to mitigate some of these outcomes.
Inertia is a term that we are well familiar with in South Africa. Brent, your question for the Naked Scientist.
Hi, Dr. Chris. So this has got to do with, is there such a thing as a universal frame of reference? And let me explain it in this way. If I'm in a sealed box, if there's no acceleration on me, I can't tell whether I'm moving. You know, if I stand in a train, it feels like I'm stationary. But what if I'm rotating? So if you imagine a ballet dancer spinning and her dress would rise because of the centripetal forces. But she's spinning in relation to what? So if she stands on a children's playground merry-go-round on the axis and it's spinning in the opposite direction, she's actually stationary. So I'm wondering if there's such a thing as a universal frame of reference across the whole universe.
We should call you Galileo, Brent, because that was almost word for word. I don't think he talked about children's merry-go-rounds, but what Galileo Galilei postulated. And he made that very point that we don't know where we're going and where we're moving if we don't have those frames of reference. We have to look around at the world going past us to know that we're moving. And if we can't see the world going along and you're not physically aware, you wouldn't know. I don't think there is a way of knowing for sure. I think it's a very interesting question. I need to go and have a think about that one because there may well be a clever answer. And I like your spinning idea. I read a really good book the other day by the same guy who wrote The Martian with Matt Damon in it, the film, what became the film, The Martian. And he's got a follow-up book which I was sent, and I read it and I interviewed him because it was brilliant. He used to be a computer scientist, actually, the guy who wrote that book. And it starts with the person doesn't know where they are and they have no recollection of how they got where they are. They just know they're in some funny environment, which they figure out might be some kind of spaceship, but they're not sure. It might be a prison cell. And he does, this guy, a series of experiments, dropping things off tables to work out that he is accelerating because he's on a spaceship that's actually getting faster and faster. And he's able to demonstrate that gravity, the apparent gravity, is increasing, which you would need to see an increasing gravity if you were accelerating. And so there are ways to do this, but it's quite subtle. So I'm going to take that away and I'm going to have that as homework for next time. So thank you for this week's question of the week.
And unfortunately, we don't have time for the other question about quantum, I think, physics.
Oh, good. That's good.
We'll hold it over for next
Mind
week.
you, if it's about quantum mechanics, it should be very, very small. So we should be able to get through that really fast, shouldn't we?
And we'll leave it for next week. A big thank you in the meantime. The Naked Scientist, Dr. Chris Smith, lecturer at the University of Cambridge every Friday. Huge appointment. Loads of questions we weren't able to get to this week. Some of them we'll hold over for next week. It is nearly time for news at 10 o'clock. Natalie Malcha standing by with news at the top of the hour.